Look at this geometry. It's quite complex, but a lot of insulation and pipes and different shapes that's not so easy to find an analytical solution for. So how do we actually calculate the electric field in something like these kind of GIS systems or systems that are more complex where there's no rigid shapes? It can be quite complex to model. So what I'm drawing here is the spacer separates the two sides of the pipe, as you can see here. And then inside the spacer we have a conductor, and we draw that with a grayish color. And the spacer keeps the conductor in place like this. And this geometry is quite complex because we have some gas here, for example, SF6, and we have the conductor, which has a different permittivity, and we have this spacer with a different permittivity too. That could, for example, be epoxy. And all of these different layers have different geometrical shapes and different potentials. So finding an analytical solution for this is not the easiest with differential equations and so on. So what we can do is we can use another method called the finite element method, or FEM for short. And the finite element method models these complex geometry in a way by only doing the models and then assigning some boundary conditions. So we model the geometry and then we assign some boundary conditions. And one way to do this is by 2D. So let me draw the same system as over here, but in 2D. So I'm drawing the pipes now, the outside of the pipes, and they are usually grounded. So I'm drawing grounding symbol here on both sides. And inside we have the pipe. I'm gonna draw that in gray again. So we have the pipe inside here. And then we have the spacer. So the spacer is what keeps the pipe in space, you could say. And let me draw that just with a different color. And like that. So this is the spacer, and it could look something, oh, try again, could look something like this. And these have different potentials. So let me write C here for the conductor and S here for the spacer. And this is this one is grounded. Let me just write G grounded. We have different potentials. The boundary condition for this is that here we have 0 volt assigned. So we know this potential. And here we have a high voltage in the conductor. These are different potentials. But how can we model this with the finite element method? There are two assumptions that we need to take into consideration. So what you see here is you see a mesh of triangles. And what the finite element method does is that for any geometry, it divides the geometry into a mesh of triangles. And the first assumption for the finite element method that is based upon is that you see these black nodes here. Each of these black nodes have a voltage assigned. So this one could have a voltage, we call it V1. And this one could have another voltage assigned, we call that V2. And then we have this one down here, call that one V3. And what you see is that these nodes, they form a triangle. And this triangle is a plane. And what it means is that inside of this triangle, we have an electric field that is just the negative of the gradient of the voltage. So first of all, let's write the equation for the voltage, and let's write that in red. So the voltage inside of this triangle is equal in the xy plane, it's a two-dimensional plane, it's equal to slope first a1 of the x coordinate plus a2 times the y coordinate. So what we see here is that there is a potential inside of this or along the lines of this triangle, and there's no curvature. So it's not very complicated to find the gradient of the voltage. So we know that, let me just zoom out a bit. We know that the electric field is equal to the negative gradient of the voltage. And when we have this voltage here that is only dependent on two linear lines or linear lines in the xy plane with a slope, then it's pretty easy to find the negative gradient here, because then the negative gradient is just equal to minus, and then we have a1 times x plus a2 times y. And why is this smart? Well, it's smart because then it's pretty easy to figure out what the electric field is inside each of these triangles. And where do we use this? So that's the second assumption, because, okay, then we know that we have some potential in each of these nodes, and we know that the potential along the lines is linear, and we know that inside of the triangle, the electric field is proportional to the slope of the lines. Fair enough. But how can we find it for the whole system? And what is the goal of this? That's the second assumption. That's the why. So why the method actually converts to the right answer. So nature doesn't just pick random potentials. It picks the potentials to go towards equilibrium that settles at the lowest stored energy. So what is the energy of this kind of system? Oh, let me write that in blue just to make it a bit different. So the energy here of this kind of system is equal to the triple integral, which I'm writing here, and half times permittivity times the electric field, the absolute of the electric field squared, and then we integrate over the whole surface. So this is the energy of the whole geometry. And we want to find where this energy goes towards the minimum. How do we do that? Well, as we always do, we differentiate the energy of the system with respect to each of these voltage nodes. So this node here, this node here, and this node here. We go over each of these with a different algorithm. So we say d, y, I, where the I is for each of these nodes here. So this one, this one, this one, and so on for the whole geometry. Continuing. And then we go, oh, we want to find out the minimum of this. So we set it equal to 0. And this is basically how you determine mathematically how energy is distributed across it for each of these nodes. So we find the voltage at each of these nodes, and then we find the electric field inside of these. And that's how the finite element method works. So it is based on second assumption here and the first assumption here. So these are the two assumptions for the finite element method that couples it all together. And if I zoom out a bit, you can see how we have our geometry from before. We have the spacer, the conductor, and the outside pipe that is grounded. And then we have the triangular mesh. One thing to notice is that you can see there is some pointy edges. For example, here we have some pointy edge. And for the actual finite element method in, for example, Comsol Multiphysics, you would have a different granularity of triangles, because the slope here, when we come closer to this tip, the electric field will increase here because there's a slope. So the change in electric field strength gradually over here is higher than, for example, out here where it's not changing as much. So you would have different granularity here where it would be finer. The triangles would be finer, so they would be smaller here, for example, something like this, or even smaller. And out here where the field strength is not changing so much, you would have triangles that are not as small. This is just something to bear in mind. So let me show you how this looks like in Comsol. What you see here is the geometry for the spacer, where we have the conductor here in the middle, and here we have the grounded plane, so that would be the pipe, where the pipe is touching. And here we have the spacer inside, and here we have the SF6 gas inside. So this is the geometry that you define. Then you define the materials for each part. So we have the SF6 gas here in the space between the spacer. Then we have the epoxy, which the spacer is made of. And we have some aluminium here, which is the conductor. And each of these materials you assign a permittivity So here the permittivity of the SF6 gas is assigned as 1, and for the epoxy, you have assigned it as 5, and so on. And then what you see here is the next step, and that is defining the boundary conditions. So the boundary conditions, we first of all have the ground. So the pipe here, this is the outer pipe. This is grounded. We have grounded this side. We treat the epoxy as an ideal solid, no free charges moving through it, so charge conservation is satisfied, and the field settles at equilibrium that satisfies the boundary conditions. And then we have some electric potential here, which we have assigned on the conductor's surface, and that potential is assigned to 231 kilovolt. So quite a high potential. The next thing you would do is that you would go to study and then run the simulation where it computes. So then it would make these meshes and compute the actual. So you can see the mesh here, and then you can see the granularity of the mesh. So I've chosen extra fine, and the finer the size that we can do extremely fine, then it would be even more. And then after you have chosen the mesh size, you can go to study, and then you can update the solution. Then it computes the distribution, and then you can see the actual electric field and how it's distributed in here. So this is the electric potential we can see. And let me go to the electric field. It's this one. And let me make it a bit bigger here. Like that. Okay. So what you see is that you have the electric field from the ground, the pipe here on the outside, to the surface of the conductor. And we can see that in this space inside here, where there is a curvature, where there is a pointy edge, we have a concentration of the field where it's strongest. So here it's around 5 kV. And then from the conductor to the ground, the electric field strength gradually decreases. So to 0 here around the inside of the spacer. The way that this spacer is made is to distribute the field in a way that is better in terms of the lines and how they're distributed, so there's no too high concentrations of the field strength. This is how the actual simulation looks like in Comsol for finite element method simulation.